Hi friends, in this video we will discuss about the fluidized bed reactor with the combustion. So it is fluidized bed reactor with combustion. This I will try to model using Ansys Fluent. So in this scenario, geometry what I will be taking is I will just show it to you. So this is the geometry. Maybe I will snip it and take to paint. So from here air will be entered at 500 Kelvin, and from here I will be allowing ethane to be entered at 300 Kelvin, and there will be anthracite balls or anthracite spheres that will be present in this conical section. So as the air inlet velocity will increase, it will try to push these anthracite balls when the weight of the anthracite balls is equals to the drag force that is executed by the air inlet. So the anthracite balls will be moving into the air as if it is a weightless, right? And now this ethane will start reacting with the air which is coming in, and the reaction will happen. So due to these anthracite balls which is floating, there is much more volatility, not volatility exactly, it's much more turbulence will happen, and there is a reaction progress or reaction will happen at a higher rate, right? So this is the use of the fluidized bed reactor, and this is an outlet. So now instead of having this anthracite balls, you can also keep coal and just make air inlet, so that the coal will also can ignite and coal will also combust, and all those things can happen. So this is an example case what I am taking, where air is inlet and it is an inlet from another side, and there is a fluidized bed or the anthracite balls which try to fluidize when the air inlet velocity is increased to a certain level. Okay, so I'll show you the case. So you need to go to general. So make it steady with the y as minus 9.81, because the gravity should be on. Then the weight will be acting in the downward direction for the anthracite. Then the air velocity will be, it should be sufficient enough to push the anthracite balls in the up direction. Okay. Next, try to on the multi-phase Solarian, apply. So I need to use dense discrete phase model, because anthracite balls will occupy a huge amount of volume that is present inside the cells. So in order to modify or model that volume that is occupied by the particles, we need to use dense discrete. If the particle contents is less than 4%, then you can use DPM, then need not use dense discrete. But in this case, you need to use dense discrete, because the volume fraction of the balls is high. Then go to species mass transfer. On the species mass transfer, volumetric, apply. Okay, go to materials. Here the ethane air is activated with nitrogen, water vapor, carbon dioxide, oxygen, and the ethane. Then go to Eulerian model. In the phase 1, it should be ethane air. In the phase 2, you can just leave this. That will model in the DPM, discrete phase model. Okay, apply, close. Now we need to activate DEM collision. So in the DEM collision, how it is different from DPM. So in the DEM collision, there is a particle-particle interaction. So the particle-particle will be coming and colliding, and again they can leave their ways. So it's like two particles coming in these directions. They can collide, and again they can move in the different ways, but not in the DPM direction. Then the DPM, so the particle collision will not be taken into account, but only due to the stochastic or then the turbulence way, the particle collision will be taken into consideration. But here in this DEM, will have the friction coefficient and everything between these particles, which is not considered in the DPM. So all these friction coefficient or coefficient of restitution, how the particle-particle inelastic collision or elastic collision, all those things can be considered, which is not feasible in DPM. Right? Now you can see collision partners. So one is aluminum, and all of this aluminum anthracite. So we'll modify this. You need to go to injections, create an injection first. So in that anthracite, phase 2 is our discrete phase domain. So our stop time will be 1 e power minus 8. For first time step only, I just want to have this particles to be injected, so I am keeping that. And for this particle location, so I just need to, I'll be using a file. In this file, all the anthracite particles within this conical section is already present with the respective positions. So obviously when I run for one time step, all the particles will be initiated at the conical sections at the respective positions. So this is a DEM anthracite, which is a collision partner. Now you can go to this aluminum and aluminum anthracite. And if you want to have this interaction between those two, you can just click on anthracite, and you need to mention all these things when there is an interaction between anthracite and anthracite. So there will be a friction coefficient and all those values you can mention here. These are default values which I have taken with respect to the tangential contact forces law. Okay, you can keep OK. And then in the inlet, you should not take DPM as an escape, because all the particles will be leaving. So you need to take a reflect with a DEM collision partner as DEM aluminum. Similarly for gas inlet also, the boundary condition should not be escape. It should be a collision partner DEM aluminum. Okay, and here obviously the phase 1 is air ethane, in which only air should be present. So ethane fraction is 0, and remaining things are taken from the air constituents. And in the gas inlet, only ethane will be present. So that reason why I have taken the phase fraction or the velocity as 0.01, temperature is 300, and the fraction of ethane is 1. Similarly, you can see in this, temperature is 500 with the velocity of 0.03 I have taken for the air as an inlet. Okay. Now you will need to take the initialization. So click on initialize. With all the temperature inside is 500, and entirely it is occupied with the oxygen with 0.26. There is no phase 2 present initially. Then you take 1 e power minus 8 as a time step. I'll be clicking on calculate. For the first time step, I'll just show it to you how exactly it looks like. So I'll be stopping at the end of the first time step to show you the discrete phase or DEM particles, that is anthracite particles, how exactly they look like. So go to graphics, go to particle tracks. So you can see these are the particles, how they are placed at the respective centroid locations. And when this particle to particle collides, so there will be a friction coefficient and the tangential forces according to that the particle moves. So in order to have a spherical look, you can use this spherical attributes, and if you want to increase the size of the spheres, you can do this. Now if you click and save display, the size will be increased. You can see it, right? Yeah. So now I'll click on decrease the time step size. It's sufficient to run the calculation. I'll show you how exactly the results will look like. So I have already created a mesh also in order to have an appeal. So this is a mesh with faces what I have clicked. Now I'll go to an scene with activating both of these things. So it will look like this, and after that I'll be going to the solution animation, and I'll create an animation for this scene for every 5 time steps and click on OK. So now after clicking on calculate for every 5 time steps, this animation will be saved. Now I'll run calculate, and after maybe 1 or 2 hours I'll show you the results. You can, if you want to have to change the activation energy or pre-exponential factor of the ethane reaction, so you can go to finite rate and you can change here the values, pre-exponential factor, activation energy here, and you can run the simulation. Or if you want to integrate more number of reactions also, you can increase the total number of reactions and you can integrate more number of reactions here. So I'll just show you the animation, how exactly it's look like. So you can see, so it is getting fluidized, velocity is making the particles to move up. Right, and similarly if you want to see the reactions and everything also, you can go to counters and check the ethane fraction across this plane, and you can reduce the count instead of having the global range. So you can see it is where the ethane is coming and interacting with oxygen and all those things. Yes, you can have these reactions and everything in place, and you can run for more number of time steps in order to view the results more perfectly. Yeah. Thank you, and if you have any queries, you can drop a mail.